Hi everyone, welcome back to Math 256. This is Scott. Let's get started. So what we are now going to look at is section 2.3, which is the last section of chapter 2 that we'll be discussing, and here we'll just be looking at numerical methods for systems. So as we mentioned in a previous section, we can't use numerical methods or graphical methods to analyze higher order differential equations, but we can convert them into systems. And it turns out if we have a system of first order differential equations, we can actually adapt any of the methods that we have studied so far for just ordinary differential equations into systems of ordinary differential equations. So that's a note. We can adapt any of the methods we use for first order ODEs, ordinary differential equations, to numerically approximate the solutions of systems of first order ordinary differential equations. So let's start by just discussing what the setup here is, and then we'll focus in on one method in particular, Euler's method. So the setup, there are always a few ingredients that we need to have. One, a system. Technically, what we're about to say applies to systems with more than two variables, but we will stick with just two variable systems because those are the most common application. So remember, systems involve essentially the assumption that x and y are individually functions of some parameter t, and that the derivatives of x and y are some relationship between x, y, and t. So we can just write this as saying, when you say some relationship, you can specifically call it a function of t and x and y. So we're just basically indicating what each of these is going to depend on. So it does not depend on any extra derivatives or anything like that. This is first order, so the highest derivative we see is just going to be the first derivative. And then the same thing goes for y, and we'll just call that g of t and x and y. All right, 2. We need to have initial conditions. So x of some initial t value is equal to some initial x value, and y of some initial t value is equal to just some y value. And then 3, we need a step size in any case. H. Now, every numerical method relies on using some trick that involves the differential equation to get an approximation for the slope that will help us go from one function value to the next. And the same is true here, it's just that we need to have an approximation for the x and an approximation for the y. So just as a note here, these represent the rates of change of x and y with respect to t. That's what it means to be a derivative after all, is to be an approximation or to be the value of the rate of change. So based on that thought, if we want to go with the simplest way of modeling a system numerically, we can just adapt Euler's method. So Euler's method for systems. So essentially here, the philosophy is basically the same as taking Euler's method individually, just for the x and for the y. So the idea is to take the first value of t, x, and y, I guess values of t, x, and y, plug them into, first off, f, and that's to get the rate of change of x, and g, and that's to get the rate of change of y. And then we are going to take those rates of change literally and just get the next x and the next y by just stepping that far in the x direction and that far in the y direction. In the next x value, will be based on the change in x, let's just put it that way. The next y value will come from the change in y. And then as for the next t value, that's just one step size later. And then just the next t value is just whatever the original one was plus h. And then we just repeat the process. Okay, now let's flesh that out a little bit. So to put it more precisely, we can just say m x I, or I plus 1, let's say. All right, actually, I'll just say, I'm just going to do a little audible here, change the letters. I'm going to say L and K, so I don't have to use the subscripts. So L sub I plus 1 is going to equal F T sub I, X sub I, Y sub I, and this will be the rate of change of X. K I plus 1 will be the same thing but with G. So previous T value, previous X value, previous Y value all get thrown into the soup that will determine the change in the Y. And then the next X value just comes from taking the previous X value plus step size times the rate of change. So this is, in other words, how fast it's changing. The next Y value will be previous Y value plus H times K, so I plus 1. And then the next T value will just be the previous T value plus H. Now, geometrically, what this represents geometrically, let's say right here, let's say that this represents the x sub I, y sub I. Then we figure out how far the x is changing and how far the y is changing, and that basically makes it almost like a vector. And in fact, not almost like a vector, exactly like a vector. And this is going to be the change in x, I, and this is going to represent the change in the yi, and each one is basically just dictated from above. So it's just previous xi plus h times li, and this is previous yi, oops, plus h times ki. I should say ki plus 1. So then what that gives us is and here we can't see the t, but the t represents essentially how much time has passed getting from this point to this point up here. So this does have a very vectorial look to it, and we can actually represent these by vectors, as we'll see in a bit. But essentially, We just figure out how much each thing is changing. Let's just try to do this very. So we're going to try this very with a very simple example because this is like I said a rather ungainly system to do by hand, but we'll just try it with something simple to start with, and then we'll see how we can get technology to help us out. So let's take as an example x prime is equal to x plus 4y, y prime is equal to x minus 2y. Let's take as our initial conditions x of 0 equals 6, y of 0 equals -1, and we'll just take as our step size h equals, we'll just say h equals 1/2. And what we'll just do is make ourselves a nice little table. So our table is going to have I values representing which stage in the process we are now on. So we'll start with I equals 0 to mean the initial condition. We're going to have the xi, the yi, we'll have the li plus 1, and the ki plus 1. Then we'll just call it change in xi, which is h times L I plus 1, change in yi, which is h times k I plus 1. And we'll just do this for a couple of values, because as you're going to see, the values get pretty big pretty fast when we're doing this. Okay, so to start with, we just have our initial conditions. So x starts out being 6, y starts out being -1. All right, and now to figure out the first L, we just take the x and the y and we plug them in to the formula here. So so if I put 6 plus 4 times -1, that's going to be equal to 2. And here I'll just put a little asterisk for commentary. So this is 6 plus 4 times -1 equals 2. All right, and then for the y value, we just plug in the x, we plug in the y. So we have 6 minus -2, so that's going to be 8, and we'll just label for commentary purposes. So this is equal to 6 for the x minus 2 times -1 equals 8. Okay, and now for the changes in the x and the y, that's just h times li, so that's a half times li, so it's just going to be 1. And for the y, that's going to be 1/2 times the 8, which is going to be 4. Now here, actually I should have put in a column for the t. Actually, I'm going to go ahead and retroactively do so. Apologies if this makes it difficult if your column was not so easily adapted. I apologize. Okay, and the next one out, so the next step, and really you don't even need the i's really, what you need are the t's. So the next step on the t is going to be 0.5. For the x, the next step on the x is going to be the previous x plus the change in x, which will now make it 7. And if I label that, so then that is just 6 plus 1 equals 7. For the new y value, we're going to have -1 plus 4 equals 3. And that'll be our last bit of commentary, the last number that required filling in here that we haven't yet seen an example of. This is equal to previous y plus change in y. And then from then on, we would just iterate the process. So you take the x and the y now as given, and you plug those into the differential equation to get the new quote unquote slope, but it's the slope with respect to t. And so in other words, the rate of change of the x and the rate of change of the y. So if I put this in here, I would have 7 plus 4 times 3, which is going to equal 19. Here I'm going to have 7 minus 2 times 3, which is just going to equal 1. And then that means this one is going to be 19 divided by 2. So that's going to be 9.5. And this one is going to be 1 divided by 2, which is going to be just 0.5. And that'll be about where we'll end things here. We'll get the next x, the next t, the next x, and the next y. Next t, it goes up by a half each time, so it goes from 0.5 to 1. The next x takes the previous x and adds this new quantity to it, and so we're going to have 7 plus 9.5, so that's going to be 16.5. And the next y is going to be the previous y plus the change in y, so it's going to be 3.5. And then we would just proceed. We would just proceed in like manner, and so on. Okay, so that is a process. It can be continued. It can be continued indefinitely, particularly when you have a computer doing your dirty work for you. In particular, what this would mean then is that our estimate for x of 1 is approximately 16.5. For y of 1, it would be approximately 3.5. Okay, and we would repeat this, like I said, indefinitely. And if we wanted a better approximation, we could use a smaller step size or a more sophisticated method. But this is essentially what we are going to try to do by hand. We'll see how to do this by computer in a second. But first, I want to discuss some other elements of this whole process. So now let's talk about another way of writing these things, which we'll see and we'll be adopting pretty regularly starting next chapter. Oh, by the way, I withdraw my previous remark. This is not the last section of chapter 2. I'm not thinking. There is one more section of chapter 2 that we're going to talk about. So ignore that first statement that I made. So vector notation. So one thing that is going to be a common practice for us, and is definitely a common practice in the world, is to represent systems of equations in a column vector format. we can represent systems and their solutions in column vector format. And in particular, if we write the x with a little vector indicator, so a little arrow if you're a human, or other notations such as an underlining, something like that for humans. And then for textbooks, just a bold typeface is what we use. So x of t, this represents the column vector x of t, y of t, and then x prime of t, or dot, either way. This represents x prime of t, y prime of t, and initial conditions could be represented as x of 0, and that would just be like x of 0, y of 0, like so. So for example, x prime equals, so x plus 4y, y prime equals x minus 2y. This could be represented quite commonly as x prime is equal to, and we usually suppress the t. We would often write this as either x plus 4y and x minus 2y, or if we utilize the way we can write these, since these are all common constant coefficient expressions, we can also write this as 1, 4, 1, negative 2, so just the coefficients, and then times xy. So these are all common ways that this might be represented. Now, we will learn in this class how to solve a wide variety of these systems of equations, particularly ones of this form. And so there are sometimes analytical solutions to these things, and when there are, we can check whether a proposed solution, or we can check how accurately our numerical approximation fits the solution that we can find analytically. So this is what you'll see on the homework. So note, if we are given a solution to an initial condition, we check it, or we can check it if that's what's asked for us. We can check it by converting it out of vector format. So solutions will typically be given in vector format. and plugging the pieces into the system. Oops, to confirm that they fit. Then we can compare the results of numerical methods to see how accurate they are. So this is what your homework is going to largely consist of, and let's just see how this would play out. So one way we can see this would be something like this. We'll take that same example here, and we've already calculated a little bit of Euler's method. Bluffton will help us calculate some more of it, and then we can see how they stack up against the real solution that I'm about to give you. Right now, I'm just giving it to you out of thin air, but by within a couple weeks, you'll know how to find it for yourselves. That's 2y, so same system, and we're going to say x of 0 equals 6, y of 0 equals -1, and then here are the things we can do. So first, check that x of t equals, and now in vector format, I'm going to give you a proposed solution to this initial condition that we will check. So x of t equals 2e to the negative 3t plus 4e to the 2t. And then the next, so that's the first row. The next row is negative 2e to the negative 3t plus e to the 2t. So that's our second row. So check that this is a solution to the initial value problem. All right. So part of the exercise here is just to translate it from this unfamiliar format into something we can hopefully try to understand a little bit. So here, let's just untangle this. What is x of t? Well, x of t is whatever is in the first row, and so it's going to be 2e to the negative 3t plus 4e to the 2t. And then y of t is equal to, so then that's just going to be negative 2e to the negative 3t plus e to the 2t. So to check this initial condition, or to check this as a solution to the initial value problem means to check two things: that it fits the differential equations, and that it fits the initial conditions. So to check if it fits the initial, or if it fits the differential equations, let's just calculate what the derivatives would be. So these are all in terms of t right now, so that's going to be something we're going to have to deal with, but we can. So first off, when we take the derivative here, we're going to get negative 6, this is just the chain rule speaking, e to the negative 3t plus 8 e to the 2t. Remember, when you are taking a derivative of something of the form e to the negative 3t, the e part stays the same, but there is an extra factor due to the chain rule of whatever the constant that's on top of the t is. And then y prime of t is going to equal 6 e to the negative 3t plus, and then here we're going to have now 2 e to the 2t. Okay, so now to check the differential equation, the question is x prime, let me put space here, equal to x plus 4y? Well, we'll just put all of these pieces into their appropriate spots and see if they all work out. So negative 6 e to the negative 3t plus 8 e to the 2t. The question is this the same as the formula for x? We can put parentheses on it and use that, plus 4 times y. So 4 times negative 2 times e to the negative 3t plus e to the 2t. All right, well, let's just see here. We don't want to go crazy over here, so let's just take our time. 2 e to the negative 3t plus 4 e to the 2t minus 8 e to the negative 3t plus 4 e to the 2t, which sure enough, if we combine like terms, is going to be negative 6 e to the negative 3t plus 8 e to the 2t. And that, sure enough, is what we wanted it to be equal to. So first it was questionable, but now this equals, it really checks out. Okay, so the x prime, that one all lines up. How about the y prime? So it's supposed to equal x minus 2y. All right, well, y prime, as we discovered, was 6e to the negative 3t plus 2e to the 2t. The question is, does that equal the expression for x, which was 2e to the negative 3t plus 4e to the 2t minus 2 times the expression for y, which is negative 2e to the negative 3t plus e to the 2t. And again, where this solution came from, that is a matter that we will be learning about later. But for now, we're just checking a proposed solution to see if it fits the bill. And so we get this, and then this is just 2e to the negative 3t. Just trying to be careful here so we don't make a mistake. Now, if we distribute that, it's going to be positive 4 e to the negative 3t. So far, it's looking pretty good. Minus 2 e to the 2t. We combine the like terms, and we finally can confirm that what we found to be y prime matches what the differential equation suggests for y prime. So combine those, we get 6e to the negative 3t. That's good. And then plus 4 minus 2 is plus 2e to the 2t, and that checks. So we are almost home free. We just have to check the initial conditions. So does x of 0 really equal 6? And does y of 0 really equal negative 1? So that's what we need to check here now. All right, well, x of 0. So so our x of 0 was 2 times e to the 0 plus 4 times e to the 0, which sure enough does equal 6. E to the 0, recall, is 1. And y of 0, so that's negative 2 e to the 0 plus just e to the 0. Is that equal to negative 1? That's going to be negative 2 plus 1. Check. All right, it is confirmed. It is a solution. All right, well, if we have the solution actually legitimately found, then we can find the actual exact values of the x and y at certain values of t, and then we can use that to compare the results of Euler's formula, or Euler's method, I mean, with what we have discovered. So A. Use Euler's method with h equals 0.5. To get values for t equals 1, 2, and 3, let's say. And compare these with the formula. All right, and then B, we can say repeat with h equals 0.1. All right, well, we can, so what we can do here is switch over to technology, and we can use the technology to actually do both parts of these. So let's say formula, and Euler. And we'll say, so let's make a little table here. And t is 1, 2, and 3. All right, well, so technically we already did find the Euler's method values for t equals 1. So I guess we might as well put that. So x equals what did we find here? So going back to that page, we found that when t equals 1, x equals 16.5, y equals 3.5. But we're not going to continue drawing that out, and we're certainly not going to do it 10 times to get this by hand. Instead, we're going to switch over to Bluffton and see what technology can tell us for these values. All right, here I want to first calculate the actual function values for those values of t, and so just an easy way to do this, if you're at your computer anyway, is you can just do it in Desmos. I'm going to just do f for the x function, and I'll just do y or g for the y function. So it's just 2e 2e to the negative 3t plus 4e to the t, and I'm just doing e to the 2t, and I'm just doing this so that I've just got a formula here for the x coordinates and a formula here for the y coordinates. So this one is going to be negative 2e to the negative 3t. Oops. 3t, and then plus e to the 2t. Oops, it's not obeying my my typing. Okay, so now I'll just do f of 1. Oops, f of 1, and I get 29.655 for the x. I'm just going to note this on the paper. So 29.66. And for the y, we get 7.29. And now I'll just plug in the 2, and you can do this in a more compact, efficient way if you want. It's just a way that works. So 218.40, let's say. And then g of 2 is 54.59. And then finally for 3, it's 1600.71 or 1613. And we have here 54. Oh, I haven't done that one yet. So notice these values are getting quite large, quite fast. This is another reason why we don't want to do it by hand. So 403.43. Okay, so much for the exact values. Now we switch over to Bluffton, and let's see what it can tell us. All right. One of the good reasons to find those values first is it also will help us to set appropriate values for the x and y axis here, because Bluffton does not project much beyond what is displayed on its window. So we put in our differential equation, and we have x plus 4y, and we have x minus 2y. Now we don't care about these values. We'll just go x from 0 to the biggest x value we had. Looks like it was in the 1600s. So 1613 was what it said on Desmos. So I'll put 1615 on this one, and it takes a second for Bluffton to catch up on that. It's not it's not within its wheelhouse to deal with numbers that big. and 403. So I'll just make it 405. Okay, so that's what our slope field looks like for our actual value here. And now for the my y values, my initial y condition is not going to be on the window here, so I better make the lower bound of the y's a little bit lower there, just so it'll be on here. And now we'll have 6 and -1. Okay. And this is, we want it to be Euler, we want it to be 0.5. And by the way, we don't care about this this old song and dance anymore. This was just on there by default, so we don't care about it. All right, so then we'll just hit submit and see what we get. All right, so it looks like pretty much a straight line going up that way. Looks like it's fitting the arrows pretty well, but of course we've got a pretty wide window on this. Now, if we go to the numerical solution table here, you can see that we can get the t's and the x's and the y's up through the values that are displayed on the actual graph, as well as some going backwards in time. So here for the Euler method, when it got to 1, it agreed with what we had by hand. That's nice to see. One would hate to see otherwise. So these values are in agreement with us. And then when it gets to 2, what do we have? For x, we have 64.13. And for y, we have 15.88. And then when it gets to 3, we're going to have 256. So it's quite different from what Desmos gave us. 256.03, and then 63.97. So these values are quite a bit lower than the values Desmos gave us. And in fact, so much lower. So make sure there wasn't a typo. Nope. All right. Phew. All right. And that just goes to show you that Euler's method has a lot of error. And then if we repeat with a lower h value of 0.1, let's see if that gets us any closer. So now we can scroll down. So when we get to 1, our x value is 24.82. And our y value is 6.13. So that's quite a bit closer to what the formula said, if you'll compare them. And then at t equals 2, we'll get 153. For the x, so I'm just looking down at the table there, 0.35. And then for the y, I get 38.34. So again, closer to what the formula said, but starting to get a little bit off. And then for t equals 3, got to scroll down a little bit here. And these are the numbers. So I have 949. So a lot closer than the previous one, but still not that great. 949.51. and then 237 point. So notice it's still pretty far off from the values of 1600 and 400 for the x's and y's at t equaled 3. So if we look here, when t equaled 3, those were what we were supposed to be getting as our x's and y's, and we're getting far less than that. Okay, so be it. But now let's take a look at what the Rumakuda method would give us. So submit that. And at its 2 value, it's 218, which matches the formula pretty well. At t equals 3, it's 1613, which again matches the formula mighty well indeed. And actually here, if we wanted to graph the formula, we could do so. If you look at the options that are available for putting a graph on top of this slope field, it gives you 3 options. You can either put the function in directly, you can put a polar function, or you can put this parametric form, or you can also put an implicit equation. So here, the way we would enter this is we would first put in the x value. So it's 2 e to the negative 3t plus 4 e to the 2t. That was the x. And then for the y, so it's just in brackets, and then you put a comma. So it's negative 2 e to the negative 3t plus e to the 2t. Bracket, hit enter, and let's make it a different color from the one we see there. Get blue. And we'll just make it go t equals 0 to 3. And you can see that there's essentially no daylight between them. If we switch this back to Euler, then they're quite a bit closer than we had any reason really to expect. H equals 0.1. At h equals 0.5. So they look a lot closer, but that's just because our thing is zoomed so far out that it's hard to even see. And then in particular, so t equals 0 to 3. So that takes us all the way out to here. And then at h equals 0.5, we submit that. So even there, it's not really showing us the vast difference that we would expect to be seeing between the x and the y values. And part of the reason for that is that as long as the x and the y values are still in the proper proportion to each other, it's hard to tell from the trajectory on the phase plane here if it's not actually fitting it at the same t values. So what's really going on in this one, the reason why it looks so close, is because the x and the y values are both going up in the same proportion that they should be according to the other one. It's just that they're not as far along the curve. So in particular here, we are not going to be, the t values won't be corresponding. So we can't just look at the graph to exactly determine this, because this is something that would only come out from a more detailed analysis of the actual individual functions for x and y. But there we go. That's how we can do that. So back to our paper where we can sum it all up. Okay, so while the technology was giving us the answers, I jotted them down over here so we can look at them and compare them. And you can see that with the h equals 0.5, we have quite vast differences individually between the x's and the y's from the formula versus Euler's method. And with h equals 0.1, they're definitely a lot closer, but still they the errors start to pile up. And this will generally be the case, but if we were to do Runge-Kutta, the solutions are quite close indeed. It's a much more accurate system. All right, well that's how we can do that. So thank you for joining me for this episode of Math 256. I'll see you at the next one.